Welcome to Chapter 2, Hardware and I/O Verification. This chapter is your practical bridge between the design office and the physical plant. Here we emphasize that a control system isn't ready for functional testing until every single I/O point is physically tested and confirmed. The process ensures that what's designed on paper truly works in the real world, preventing costly mistakes and ensuring safety. We'll walk through digital and analog input-output verification, signal simulation, troubleshooting, and the final sign-off checklist. Let's begin by understanding why thorough I/O verification is critical for successful commissioning and safe operation. Digital inputs are the eyes of your control system, reading the state of field contacts like limit switches, push buttons, or motor feedbacks. These devices convert 24 VDC signals into true or false values, forming the backbone of automated decision-making. Understanding how digital inputs work is essential for accurate system operation. In this scene, we'll explore how these signals are processed and why their reliability is vital for both safety and performance. Let's see how digital input verification starts the journey from field device to control logic. Digital input verification procedure involves teamwork between the field engineer and the control room engineer. The field engineer physically operates the device, such as toggling a limit switch, while the control room engineer observes the corresponding variable in Compact Control Builder (CBM) for state changes. Additionally, the module's LED should light up, confirming the signal's journey from device to software. This hands-on process ensures that every input is accurately mapped and responsive, laying the groundwork for reliable system operation. Normally closed NC contacts are standard for safety signals like emergency stops and pull cords. In a healthy state, NC contacts read as true. If the wire breaks or the sensor trips, the input drops to false, signaling a safe fault state. It's crucial to ensure that CBM logic correctly inverts these signals so the system responds appropriately to faults. This understanding is key to designing safe and reliable control systems, especially in environments where safety is paramount. Digital outputs are the hands of your control system, sending 24 VDC signals to energize field devices like motor contactors, solenoid valves, or horns. These outputs directly control physical actions in the plant, making their verification critical for safe and effective operation. For testing, safety precautions must be taken to ensure that the equipment is clear and safe to operate. Let's explore the basics of digital output and why proper verification is essential. Digital output verification procedure starts with safety. You must have a permit to test, ensure mechanical isolation, and use a field spotter to physically verify that the equipment is clear. The control room engineer then forces the do variable to true in CBM, and the field spotter confirms the device energizes. After verification, the engineer removes the force. This process ensures that outputs are mapped correctly and that safety is never compromised during testing. Forcing outputs is a powerful but dangerous commissioning tool. The guide establishes a critical rule. At the end of every day, you must check the force list in CBM and remove all active forces. Forgot forces, especially on safety interlocks, can cause severe accidents. Proper force management is essential for maintaining system integrity and preventing unintended operations. Let's understand the importance of this rule and how it safeguards the commissioning process. Analog inputs read continuous signals from field transmitters, such as pressure, temperature, flow, or level sensors. These signals typically use the 420 MA standard, allowing precise measurement of process variables. Analog inputs provide the detailed information needed for advanced control strategies and monitoring. Understanding how analog inputs work is crucial for accurate system performance and troubleshooting. Verify analog inputs. Disconnect the field transmitter and connect a MA loop calibrator directly to the AI module terminals. Inject known values 4, 8, 12, 16, and 20 MA corresponding to 0%, 25%, 50%, 75%, and 100% of the range. The control room engineer checks that both the raw value and the scaled engineering value in CBM match the injected current perfectly. This procedure ensures that analog inputs are calibrated and functioning as intended. Alarm testing is a vital part of analog input verification. Injecting 3.8 MA triggers the underrange alarm, while 20.5 MA triggers the overrange alarm. The control room engineer must confirm that these alarms activate correctly in CBM. Proper alarm testing ensures that the system responds to abnormal conditions, protecting equipment and personnel from potential hazards. Analog outputs send continuous 420 MA signals to drive variable devices like control valves or variable frequency drives, VFDs. These outputs allow for precise control of process equipment, adjusting positions or speeds based on system requirements. Proper verification of analog outputs ensures that the control system can accurately manipulate field devices for optimal performance. Verify analog outputs. Put the associated PID loop in manual mode. Force the AO to known percentages 0%, 25%, 50%, 75%, and 100% in CBM. A field engineer measures the MA current in the loop with a multimeter and physically confirms that the valve or VFD moves to the correct position or speed. This procedure ensures that analog outputs are accurately mapped and responsive to control command. Field engineers rely on specialized tools for signal simulation and verification. These include MA loop calibrators like the Fluke 787, HART communicators for smart transmitters, and RTD thermocouple simulators. Using these tools, engineers can inject and simulate signals to test system responses, ensuring that all hardware and software components interact correctly. Forcing signals in Compact Control Builder (CBM) can be done in several ways: via the watch window directly on the FBD logic sheet or at the hardware I/O level. Forces survive a warm restart of the PLC but are cleared during a cold restart. Understanding these methods is crucial for effective commissioning and troubleshooting, allowing engineers to simulate and test system behavior under controlled conditions. Tracing physical wires is a core requirement in I/O verification. The guide outlines the path you must follow, from the field device terminal to the local junction box to the marshalling cabinet terminal strips to the S800 I/O module terminal base and finally to the software channel in CBM. This thorough tracing ensures that every connection is correct and that signals flow as intended from field to control system. Comprehensive I/O troubleshooting is essential when a point fails verification. The guide provides diagnostic steps for common issues, including wrong channel mapping, open circuits, short circuits, sensor failures, and grounding or EMI noise. Effective troubleshooting ensures that problems are quickly identified and resolved, minimizing downtime and ensuring system reliability. Wrong channel mapping occurs when a field device operates, but the wrong tag changes in SCADA. This issue is fixed by correcting the physical wiring or the CBM channel mapping. Ensuring accurate channel mapping is crucial for reliable system operation and prevents confusion during commissioning and troubleshooting. Open circuits cause digital inputs to read false or analog inputs to read 0 MA. Diagnosis involves measuring voltage or current across terminals from the module to the junction box to find the wire break. Identifying and repairing open circuits restores proper signal flow and ensures accurate system operation. Short circuits are indicated by a blown fuse and a red fault LED on the module. They are often caused by water ingress or damaged cable insulation. Detecting and addressing short circuits is vital for preventing equipment damage and ensuring system safety. Sensor failures are diagnosed when the analog input reading is stuck at a constant value regardless of process changes. Confirm this by simulating a signal. If the PLC reads the simulator correctly, the transmitter is dead. Identifying sensor failures ensures that faulty devices are replaced promptly, maintaining system accuracy. If analog signals fluctuate wildly, there is likely a ground loop or electromagnetic interference (EMI) from power cables routed too close to signal cables. Proper grounding and cable routing are essential for stable signal transmission and system reliability. Addressing these issues prevents erratic behavior and ensures accurate measurements. The chapter concludes with a strict sign-off checklist to ensure everything is documented before functional testing begins. Key steps include removing all simulation equipment, reconnecting all transmitters, verifying all alarms, and ensuring no active forces remain in the PLC. This checklist guarantees that the system is ready for safe and reliable operation. Let's walk through a practical example of digital input verification. The field engineer manually toggles a limit switch, while the control room engineer observes the CBM variable and module LED. This hands-on process confirms that the input is correctly mapped and responsive, ensuring reliable operation from field to control system. Safety signals often use NC contacts for emergency stops and pull cords. In normal conditions, these contacts read as true. If the wire breaks or the sensor trips, the input drops to false, signaling a safe fault state. Ensuring CBM logic correctly inverts these signals is vital for safety. Before testing digital outputs, always secure a permit to test, ensure mechanical isolation, and have a field spotter verify that the equipment is clear. These precautions prevent accidental energization and ensure that testing is conducted safely and responsibly. During digital output testing, the control room engineer forces the do variable to true in CBM. The field spotter confirms the device energizes and the engineer removes the force afterward. This ensures that outputs are mapped correctly and prevents unintended operations. Managing the force list in CBM is a daily responsibility. At the end of each day, engineers must check and remove all active forces. This practice prevents forgotten forces from causing accidents, especially on safety interlocks. Proper force management is a cornerstone of safe commissioning. Analog input verification uses a MA loop calibrator to inject known values into the AI module terminals. The control room engineer checks that both the raw and scaled values in CBM match the injected current. This process ensures that analog inputs are calibrated and functioning correctly. Alarm verification involves injecting 3.8 MA for underrange and 20.5 MA for overrange alarms. The control room engineer confirms that these alarms activate in CBM, ensuring the system responds to abnormal conditions and protects equipment and personnel. Analog output verification involves forcing the AO to known percentages in CBM and measuring the MA current in the loop with a multimeter. The field engineer confirms that the valve or VFD moves to the correct position or speed, ensuring accurate control. Field engineers use simulation tools like MA loop calibrators, HART communicators, and RTD thermocouple simulators to test and verify signals. These tools enable engineers to simulate real-world conditions and ensure that the control system responds accurately. Forcing signals in CBM can be done via the watch window, FBD logic sheet, or hardware I/O level. Forces survive a warm restart but are cleared during a cold restart. Understanding these methods is essential for effective commissioning and troubleshooting. Signal tracing follows a specific path: field device terminal, local junction box, marshalling cabinet terminal strips, S800 module terminal base, and software channel in CBM. This process ensures that every connection is correct and signals flow as intended. When an I/O point fails, verification followed diagnostic steps for wrong channel mapping, open circuits, short circuits, sensor failures, and grounding or EMI noise. Effective troubleshooting minimizes downtime and ensures system reliability. Correcting channel mapping involves fixing physical wiring or updating CBM channel assignments. Accurate mapping ensures that field devices correspond to the correct tags in SCADA, preventing confusion and errors during operation. Repairing open circuits involves tracing the signal path and measuring voltage or current across terminals. Once the wire break is located, repairs restore proper signal flow and system accuracy. Resolving short circuits involves replacing blown fuses and repairing damaged cable insulation. Preventing water ingress and ensuring proper cable routing are essential for system safety and reliability. When a sensor fails, simulate a signal to confirm the issue. If the PLC reads the simulator correctly, replace the faulty transmitter. This ensures that analog inputs remain accurate and responsive to process changes. Address grounding and EMI noise by ensuring shields are grounded at a single point and routing power cables away from signal cables. These steps prevent signal fluctuations and maintain system stability. Before functional testing, review the completion checklist, remove simulation equipment, reconnect transmitters, verify alarms, and ensure no active forces remain in the PLC. This final step guarantees system readiness and safety. Documenting every step of I/O verification is crucial for accountability and traceability. Proper records ensure that all tests are completed, issues are resolved, and the system is ready for functional testing. This practice supports safe and reliable operation. With all I/O points verified, alarms tested, and forces removed, the system is ready for functional testing. This preparation ensures that the control system operates as designed and that any issues are addressed before live operation. Successful I/O verification relies on collaboration between field engineers and control room engineers. Clear communication and teamwork ensure that every device is tested and every signal is confirmed, supporting safe and efficient commissioning. Chapter 2 covers essential concepts in hardware and I/O verification, including digital and analog input-output testing, signal simulation, troubleshooting, and completion checklists. Mastering these steps ensures that the control system is safe, reliable, and ready for functional testing. Conclusion: thorough hardware and I/O verification is the foundation of safe and reliable control system commissioning. By following the procedures, using the right tools, and maintaining strict documentation, engineers ensure that every signal is tested and every device is ready for operation. These best practices protect both personnel and equipment, setting the stage for successful functional testing and long-term system performance.